Hey everyone, welcome into this lecture on exponential growth. This is our first lecture video in the growth model lecture series here. It's lecture 9 of the semester. So in this lecture, I'd like to talk about a differential equation. Now we're going to study differential equations in much more depth later on in the semester, but given the tools that we have right now, we can solve this kind of straightforward one. This one says dy dx, so the derivative of y with respect to x, is equal to k times y for some constant k. All right? And the idea with a differential equation is that we want to try to solve this equation for this unknown function y. So this function y is unknown, it's a function of x, and we want to try to solve for y in terms of x, right? So find a function that obeys this relationship. And this relationship says that the derivative, or the rate of growth, the instantaneous rate of growth of our unknown function y, is proportional to the value of the function itself, right? To the output of the function itself. And the constant of proportionality here is k, and this k is sometimes called the growth rate. Now, if k, so I'm going to write it this way, it's called the growth rate if k is positive. It's called the decay rate, or sometimes it's just you say you have a negative growth rate, right? But it's called the decay rate if k is negative, and nothing's happening if k is 0. If k is 0, there's not even a y over here, right? It's just equal to 0. So this is the situation that we want to try to solve. I'm going to add some other information to this, actually. So let's solve the differential equation first, and then I'm going to add another piece of information for us here. This is our first step, right? So what can we do? Well, the idea here is that the function y is an unknown function of x, right? But x is another variable. It's an independent variable, and k is a constant. So we can take our differential equation here, which, by the way, right now probably should be called a derivative equation because it relates the derivative of the function to the function itself, the unknown function. And what we can do is we can kind of get the variables isolate the variables on their own side of the equation. So we can multiply through this entire equation by dx. In this scenario, you're thinking of dx as a differential, a tiny, tiny change in x, right? A tiny change in x. And on the other hand, you can take this y and you can divide through over to this side, right? And so what's the resulting equation? Well, now you end up with an equation that says 1 over y dy equals constant k times dx. And this is where the name differential equation comes from, because now you've got a differential equals a differential, right? These two differentials are equal. And the differentials, we know, I mean, we might not have 100% built our intuition yet of what a differential is, but in some sense, a differential is something that can be integrated, right? And so at this point, we can remove the derivative. And again, so I'm being a little loose here, but we can integrate out, right? We can integrate this entire equation. So we can integrate both sides, and when the differentials are equal, then their integrals are equal up to a constant, right? And when we look at this, we see integral, or antiderivative, I should say, of 1 over y dy. What's this? Well, this is the natural log of the absolute value of y. And on this side, k is a constant. So the antiderivative of a constant is just a linear function, k times x. And from each of these, we should obtain a plus c, right? If you're taking antiderivatives, you should get a plus c. We can just group those together and put the entire plus c on this side. So we get this equation, all right? Remember, though, our job was to solve for this unknown function y. Y is the unknown function that we want to solve for. So how are we going to do that? Well, we see we've got our y inside of a natural log, and based on our review that we did, we know that you can the inverse function of a natural log is the exponential function. So we can take and the exponential function is 1 to 1. It's a nice function, right? So we can take the exponential of both sides of this equation and see what happens. So on the left-hand side, the exponential and the log cancel, and we're left with the absolute value of y. On the right-hand side, we have an exponential of a sum, right? The sum is in the power of the exponential. And I'm sure you remember your exponential rules say that you can break up a sum in the exponent to be a product of the bases down below. So this can be written as e to the k times x times e to the c. All right, so this is a property of exponents. At this point, this e to the c, right, this e to the c is unknown. This is an unknown constant. Why? Because c itself was an unknown constant from the integration, and e to the c is just the exponential of that. a couple things happen here. Number one, no matter what c was, even if c was negative here, e to the c is positive. And over here we have our absolute value bars that are positive, right? We want to kind of take care of both of these at the same time. So remember, our job is to solve for y, not for absolute value of y. And so it's possible that y could be negative, right? But if y is negative, e to the kx can never be negative, no matter what x is or what k is, right? Remember, k, we're going to assume k was given to us, right? But even if k is negative, e to the kx is not going to be negative. It's always going to be positive. So what can happen, though, if this function y was going to be negative, what would have to happen to this right here, this constant? Well, it would have to be negative. So what we can do now, this is a little loose here, but we can drop the absolute value bars, right? This is y of x, equals, and then I'm just going to replace this e to the c by another c. Now what I probably should do is call this original c c1 and call this one c2. Alright, so this is another constant, but this time this constant can be negative. Alright, and then this e to the kx, that's the kind of the meat of the function of our answer, right? There's another reason that we want to do this, though, because e to the c1 here cannot be 0 either, but k could have been 0, right? We said, I mean, up here we called it growth rate, decay rate if it was not 0, but k is allowed to be 0. It just says k is a real number in our original statement of the problem. And if k is 0, then actually this entire function should be 0, right? And the only way to allow for that is to allow for c2 to be 0. So at this point, we've now written down our general solution. So this is our general solution to the differential equation, our exponential growth problem, and notice we have the exponential function as our answer. This is the general solution, and by the way, this number c2 can be any real number. It doesn't have to be positive or anything at this point. So we've made, that's why it's a different one, right? Different than this c1 here. Alright, so there you go. There's a general solution of your exponential growth problem. If you know k, you can plug into this and you've got it, right? Now I think it's useful, it's not that hard, right, to actually integrate. It's useful to at least a few times work out the integral here to get your solution. But I said I was going to add something up here. So this unknown constant c is a little bit, you know, it would be nice if we could determine this function c2 or this number c2 explicitly, right? But it turns out that if you're only given this information, that your derivative is proportional to your function, then you don't have enough information to solve for this unknown constant. What you actually also need is you need what's called an initial condition. So for this we say y of 0, here x is 0, right? So when x is 0, y of 0 is equal to some number, okay? And this is again called our initial condition, or our initial value. And frequently a differential equation with an initial value is called an initial value problem. And like I said before, we will return to those later in the semester. But we can use this, right? So suppose we knew this. This is by the way, if you're thinking in applications, physics, or engineering, this y of 0 equals y naught, this is like an initial measurement that you've made, an initial measurement. So you've got an initial measurement, and then you've got maybe a physical law telling you what the relationship should be, right, between the variables. You've got some experimental value of k, depending on what kind of growth you're modeling. So experimental value of k, you've got an initial measurement. Here you've got a physical law, right, and then the differential equation. You should be able to find a function that models your growth. So anyway, back to this problem, right? If y of 0 is equal to y naught on one hand is a number, right? So it's a real number, then that's great. But we can also plug 0 into our function up here, right? So y of 0 on the other hand is equal to c2 e to the k times 0, right? Plug in x, 0 for x, you have to do it everywhere. E to the k times 0. Well, k times 0 is 0, e to the 0 is 1. So this is just c2, right? And at this point we see, all right, we've got y of 0 equals 0, right? Or y of 0 on both sides here. And so then on the other side we have y0 and c2. So this tells us that y sub 0 should be equal to c2, or probably in the reverse order, right? This unknown constant c2 actually, with this extra information, becomes a known constant. It becomes c2. So here's our final answer to our initial value problem. I'm going to rewrite the problem. So dy by dx is equal to k times y. There's our differential equation. Initial value, y of 0 equals y naught. this thing has the solution. By the way, now it's the solution, the unique solution, that y of x is equal to initial value, y naught, times e to the k times x. Okay, and so that is the general solution to the exponential growth problem. Now, I want to now take a moment to plot some curves where either y naught varies or k varies. So let's take a look at this. This right here is Sage Math. So this is a mathematical programming language you can ask me about if you want. But I'm going to type in some things here. So first of all, what do we want? We need to define our variables. So we have k and we have y0. These are our variables. We need to define our function. Let's first go through different values of k. All right. So let's say that y naught is equal to 1. So we'll fix that, and then we'll make our function. All right. So I'm going to call this function f instead of y, just to avoid confusion with the variables. But f is equal to y naught times the exponential of k times x. All right. That part, that's our general solution, or that's our general solution, right? And we're going to then let k vary. And so this is what we want to do next. We want to make a little loop here. So for I in range, let's do 31 of these curves. I want to plot f, so this function f, on an interval from, let's do -5 to 5. Let's make our y min equal to -10 and our y max equal to 10. This is just going to keep the window nice, a nice set of axes. And by the way, I have to go back here because the whole idea here was to make a choice, right? So we want to plot the different values of k. So we're going to substitute in k equal to, let's do this. Let's do I minus 15. That was supposed to be, that was very bad. K is equal to I minus 15, let's say, over 2. All right, so these are different values for f. What else do we want here? Yeah, it's fine. I want to make a movie out of this, so here's what I'm going to do next. I'm going to make this. I know this is not the most riveting thing to watch, but this is at least how I do this, so let's try. And then I want to do, let's say, M for movie, animate, P, and then show this. Let's see what this looks like. Hopefully this works. Cross your fingers. So this little star here means that it's computing. It's going to take a little while. Mostly the animating takes a little while. And there we go. We can see exactly what's happening. So this is, by the way, for negative k, and then it turns to positive k. So the k value, notice that right here, this point on the y-axis, this is fixed at a height of 1, and that's exactly what y naught represents, y of 0. Y of 0 equals 1 is representing the y-intercept of your solution curve. And then the change in k values, so I probably, with more time, I would have made this like print out the value of k as it goes. But as k changes, right, it affects the shape of this graph. So this is definitely an exponential curve, right, at all these different values. Notice there was a horizontal one in between there where k equaled 0. Watch this. K is 0, right? And then it turns into this positive k. But the k, the growth rate, affects how steep the graph is or how quickly it shrinks if you go in the other direction, right? So how quickly it's shrinking, that's decay, constant, and then very quick growth, okay? So that's the idea there. Let's change this around so that we are fixing k equal to 1. And then let's change it so that now we want to substitute in different values of y naught. So this should be, you can make a guess here, right? This should be, well, I'll let you think about it. You think about what this should look like, and then we'll find out if you're right. I'm just going to change the names of these. All right, so that's the only change I made, right? K equal to 1, and then the y naught is going to vary. So as this thing computes, think in your mind how this is going to change. What's going to change now? By the way, y naught's going to be 0, or it's going to be negative at some points. That looks like the same picture. This one should be looking different than this. Oh, because I animated P. See what I did there? I typed animate P. So I need to just change one thing here. equals animate. See, this is why I changed the letters. And then dot show. So this is the same one as before. I'm not going to edit this out of the video. It's good for you to see my mistakes. So we want to see PP, right? PP. And then this one should be different than that. That's the same picture we saw before. There we go. This one is different. So now look at what's happening. So as y0 changes, it changes the intersection. It doesn't really change the shape of the graph, right? It changes the relationship of where the graph intersects the y-axis. That's it. So that's the effect of the initial condition. That's the effect of the initial value, I called it, right? The initial value changes where it intersects, and then the growth rate changes how steep the curve is. So those are two examples of the growth model, and I'll leave this here and I'll see you guys in the next video.